Hello and welcome to part 3 of this series. Okay, we can write it number 3 here. And notice that I am calling it the knapsack problem. The knapsack is not the algorithm, it's the problem. The greedy algorithm is the algorithm by which we solve it. So here is the problem that we are facing, and we want to maximize the value, and we have a weight constraint, and we can choose to take an item, part of it, none of it. Okay. Also, we looked at the density of the value per the weight, and we saw in the previous video how to use the greedy algorithm to solve the knapsack problem. Now, I want to achieve two things with this video. The first one is to give you an example in the case where the items are not divisible. The x can be either 0 or 1, but not in between, okay, where the greedy algorithm may fail. Okay, so we will see an example. The second thing that I would like to do in this video is to show you an alternative representation of this problem that you might encounter in other sources and books and so on. So we'll see how to write this problem slightly differently. Okay, so let's start with an example where the greedy algorithm may fail if we have to choose either to take the item as a whole or not take it at all. So now the constraint is not going to be anymore x between 0 and 1. We are trying to now understand where the greedy algorithm may fail in the case where the items are indivisible. I have to choose xi either 0 or 1. So here is an example. I wrote an example in which there are 3 items. I can only carry 50 pounds. Okay, there are 60 total, so I need to choose which items to take. And I cannot take half an item and so on. So the greedy algorithm said, let's compute the density. 60 over 10 is 6, 100 over 20 is 5, 120 over 30 is 4. They are already ordered by their density. The greedy algorithm will say, okay, take the one with the highest density, give it 1, it's just 10 pounds, it's less than 50. Okay, the second one is this, also this is the x, okay, xi. 1 as well, I'm only at 30. Should I take the last one? Well, I would like to, but I can't, okay, because then I will have to carry 60 and I cannot carry more than 60. So if I use, okay, so I have to put here at 0. So if I use the greedy algorithm, I will have my total value will be v, okay, will be 1 times 60 plus 1 times 100 plus 0 times 120. Okay, and that will be 160. Now, obviously, we can do better than that. Okay, so if we actually set the first item to be 0, okay, so let's call it x tilde alternative. This will be 0. And the last two, the least dense ones, okay, the second and the third, I'll put 1, okay, so 20 by 30 is 50, I can carry 50. I will have, okay, so v tilde will be equal to 0 times 60 plus 1 times 100 plus 1 times 120, well, that's much better, to 220. Okay, so obviously here I'm doing better in the case that I cannot divide. If I could divide item number 3, okay, I would say, okay, the first two I only weight 30. I still have 20. I'll take 20 out of the 30, 2/3 of the 120. Okay, so the v star, where I can divide, they are divisible. Okay, so it's not here v and v tilde is where I can't break them. Then the star, the x star here, okay, I'm running out of place, but it will be 1, 1. And here I'll cover 30 and I have 20 more, so I take 2/3. Okay, that's the fractional knapsack algorithm. Okay, and here I will take 1 times 60 plus 1 times 100 plus 2/3, okay, of 120. Okay, so it will be equal to 160 plus 80. Okay, so it's going to be 240. Obviously, the best I can do. Okay, so the greedy algorithm will fail if it's not divisible, because in some cases, like in this example, I'm better off taking those with the lower value to weight density. Okay, so keep in mind that the greedy algorithm is guaranteed to give you the best when it's a fractional knapsack problem. So you can take, for in this example, 2/3 of the item number 3. Okay, here that's the x star. Okay, very good. Okay, so and there are other extensions of this problem in where you have more than one constraint. There is more than there are two kinds of weights. There is a time constraint and other machine use constraints. So there are different linear constraints and so on. But by and large, we have covered here this knapsack problem, the fractional one and the non-fractional one. Okay. The last point I want to make in this video is that you can rewrite this original problem in a different way. So this is an alternative formulation. Okay, which can be useful sometimes when you want to think about what you are doing here. So what I'm going to do here, okay, I'm going to redefine the terms in the following way. I'm going to create mi to be equal to wi, okay, times xi. Okay, so I'm asking now. You can think about it. If a certain item is the weight of a certain, sorry, if a weight of a certain item is 10, how much of that 10 am I going to take? Okay, so it's like another way to think about it. Okay, so instead of calling it 2/3, I'm going to take 20 out of 30. So my m will be 20. Okay, so we'll see. I'm still going to call density, or the density, which is going to be vi, like here, vi over wi. That's perfect. Okay, and now I can write the problem in the following way. So I can say maximize, and now I'm kind of getting rid of the xi. I'm going to choose m1 to mn. I have n items, 3 like in this example, sigma, okay, and I'm going to now write the value. Okay, so what I'm going to do, I'm going to write it as rho I times mi. Okay, so that's going to be true. Why? Because rho is v over w, m is w times x. So what is written here? Okay, it's v times x like before. Okay, so if check my algebra, but if you multiply vi over wi times xi, it's basically vi times xi. Okay, so that's the same value that I want to maximize. But now the constraints such that, okay, I cannot carry more than, let's say, capital W. So the sigma of the mi, the mass, so the weight or mass that I'm now going to take, has to be less than this W. Okay, and that's the first constraint that is equivalent to this one. But now I want to, instead of restricting the xi, I'm going to restrict the mi. Mi is going to be the lowest is 0. I'm not taking anything from that that item, or at most it's going to be equal to the weight. Okay, so I'm asking myself how much of the weight am I going to take of item I? I'm going to take. This is going to be mi. I cannot take more than capital W, and I want to maximize density times the mass here, which will give me the value. Okay, so that's an alternative formulation. And the difference is, there is no difference, but the point here is that the variables that I'm maximizing over are in a range between 0 and w rather than 0 and 1. Okay? And again, if it is an indivisible situation, the mi can be either equal to 0 or equal to wi, but can't be in between. So I could rewrite this example with this notation, and you can try it and see if you can follow this logic and replicate or rewrite this example using this alternative formulation. Okay, that's it for this video. Thank you for watching.